introduce by myself. I mean, I'm still waiting. Let me see if he will come or not. So. I think everyone knows me, and my name is Shenghua, and I am a senior sustainability research engineer at ICT. I joined here since 2015, so this is my second or third year so far. So I'm going to talk about actually a project we have been doing, 161, so it's a part of it. So it's about the high ABR on the performance of overlay and level binder mixes. Before I get started, I would like to thank all the friends and professors here, helping with the project. Akadi, Imad Akadi and Hassan, Dave, and all the students. Max, a graduate. I think Arturo is here, right? So Faisal also, Isaac, and Jose and Puneet, and of course, this project is funded by IDA. So we like to thank them, to fund us. So also the other companies help us to collect the field data. All right. Okay. This is the outline of the presentation. So it's very brief. So introduction, objective, and also two parts of the research results. One is the level binder, and the other is the overlay mixes. Of course, the summary. Okay. So a question for you guys. How many waste can you think that we can put into asphalt pavement? Right. Let's see. We have wrap. And also we have steel slag. Also we can put rubber tires, the waste. We can put in the asphalt pavement. Also we can put roof shingles. And also we can put glasses if you want. And also we can put plastics. And you can put coffee grounds if you want. Of course, some people are using that pig poop, right? I mean, even though you're having lunch now, but I don't want to mention, but still. Some people are using that waste cooking oil and also waste engine oil, right? So basically, we can put everything in one, put into the asphalt pavement, right? So is it really sustainable, right? This is actually one case in Canada. They're using that waste engine oil put into the pavement. So it was constructed in 2000, and but after only like 5 to 7 years, you see a lot of cracking. So basically, if you want to use that recycled materials, you have to make sure that they had a good quality and also good performance. So, what we should do with those recycled materials, right? Of course, I mean, when you are doing the sustainability, then you are thinking about the triple bottom line, social, economy, and also the environmental effects. But when you deal with the asphalt pavement, you are talking about performance, and performance at low temperature, right? High temperature, you don't want the rotting. And the low temperature, you don't want the thermal cracking, but also in the medium temperature, you don't want to have fatigue cracking. So what are we going to do? You're going to run a lot of testing, right? Performance test, and also you're going to verify by your field performance. So that's the overall, procedure if you want to use the recycled materials. So in our state, Illinois, now we have a lot of experience to using those recycled materials. This is just a figure in 2015. So we are using a lot of wrap and rest and also steel slag. So some just a fundamental definition here. What is ABR? Anybody knows that? Asphalt binder replacements, right? So in this is if you are looking at a mixed design. So this is ABR. Of course, this is very you cannot see here, but the ABR is that people define that as a recycled asphalt binder over the AC content in the overall mixes. So now we have 3 mixes, and for example, so we have RAS percentage and also AC asphalt content in RAS, and also we have a wrap percentage, and also you have asphalt content in the wrap. And you also know that asphalt content of the overall mixes, then you end up with that ABR calculation. So you want to calculate ABR, then you need all the information, right? So now we have 3 mixes, and even though they have the same RAS percentage, but the percentage, the asphalt content is different. So that's end up with a different ABR percentage. We have in Illinois we have a lot of old roads, so we want to do a lot of rehabilitation design, because you cannot just remove everything, right? So you're still going to build a new road on the top of that existing pavement. So you see there's a lot of distresses, a lot of cracking on the existing pavement. So what we're going to do, so that's the design that we're using right now for the rehabilitation. So you put a very thin, pretty much like less than 1 inches, the level binder course, and then you put a HMA overlay. So for each different existing pavement, you can still use the same methodology. Put a level binder and then the HMA. But still, you're going to do some milling, so trying to minimize that distresses in the existing pavement. And also, this is another example. We are just trying to remove that very bad condition, to remove those distresses through the milling. And then you put a polymer modified binder, say basically like less than 1 inches level binder course, and then put a HMA overlay. So this is our rehabilitation design method right now. Okay, so the overall, this project is trying to look at the performance of two things. One is the HMA overlay, and one is the level binder. So it looks very simple, right? So, okay, now I'm going to talk about level binder mixes performance. And, we have a lot of cracking actually in Illinois. So basically, they are reflective cracking because all the pavement that they are existing are PCC, the concrete. So we are trying to mitigate that cracking. So there's a lot of methods you can use trying to control those reflective cracking. For example, you can just do some treatment on the existing pavement. You can also put an interlayer trying to release the stress, and also you can put a level binder course. That's what we are doing right now. There's two kinds of. One is the 9.5 millimeter nominal area size, and also you can use the 4.75. Also, you can just improve that your overlay mixes, right? You are using more durable and much better quality, and also you can increase the overlay thickness. You get a very high thickness, then the reflective cracking actually going to see less. So that's the way that we control our reflective cracking. But now we are using that level binder course. So this is the mix design for the actually 5 contracts. Y03, Y02, and this is 3 contracts use the same mix design. So you can see that they are pretty much very similar in the mix design, but the only thing that you can see difference is that AC content a little bit. For the 163, you have 8% asphalt content, but the other is 7.7. The other is a very minor difference. As you can see, wrap and rest, of course, you get end up with a different ABR content. Other than that, even though for the aggregate gradation, you can see they're very close. So we are trying to compare this as a 3 level binder mixes and to see how they perform in our field. So of course, the asphalt binder, they are binders are very similar. This is a 3 binders test. Basically, they have a very close high temperature PG and also the other mechanical properties of the binders. So we did a lot of testing. Of course, we're going to get our samples, right? So I think this is Puneet. He helped get a lot of samples at asphalt plant. So we basically get all the loose mix in the asphalt plant, and then we ship to our lab, and then we do the lab compaction, and then we prepare all the mixes in our lab. So we run a lot of testing. Of course, we have a lot of equipment. So for example, this is a E-star to measure the stiffness at different temperature and different frequency. And also we have the flow number. This is a rotting test. And also we have a Hamburg we are tracking. So it's at 50 degree and to measure the rotting resistance. And also we have that moisture resistant test. That's the TSR, tensile strength ratio. And we also run our very famous test, right? IFIT test. We get a fractionation and also a flexibility index. And also we have that overlay tester. So actually the IDAT helping us to run this OT test. And also a beam fatigue test. Isaac has been doing a lot of beam fatigue tests for us. So okay, so now we are focused on the test results, like how we can actually interpret those results, right? So this is a E star dynamic modulus. If you have taken that asphalt classes, you pretty much know what is the master curve, right? So you have a lot of values at different temperature and different frequency. You are trying to convert into the master curve. So you want to compare them. So in a very wide range of frequency. So, but in this case, if you see that they are very close to each other, they're overlapping. So in this case, we found that because all the mixes are very similar at aggregate gradation, and even though you have a different APR, it's very hard to use the E star test, to distinguish all the mixes. And also, E star is just a focus on the non-destructive range, so you barely can see that difference just using the E star, of course. So, and this is a rutting resistance test. We have two methods. One is that flow number, and the other is the Hamburg wheel tracking. The difference, of course, one is that flow number is that air condition, so there's no water, and also is a unconfined test. But for Hamburg, we are submerging the water, so you basically run at the passes. So you get at a different measurement. One is the rut depth, and one is that flow number. So if you look at this is the results for the three mixes, actually they give you different ranking. For example, so if you look at flow number, just look at these three mixes. This is give you 141M has the best, the rutting resistance. But if you look at using the Hamburg wheel tracking, then you get a different ranking results. So because these two methods has a different condition, as I said, one is the confined, one is the unconfined. So and also actually the flow number had a very high variation. So even though I didn't show up here, but as a matter of fact, it has a very much like a larger the variation than the Hamburg wheel tracking test. This is the Hamburg wheel tracking. I think IDAL is using this as the very regular performance test. This is the number of passes versus the rut depth. The IDAT had a specification on this, so because level binder you are using the PG70, it's polymer modified. Even though there's a little bit difference for these two curves, actually the 1C3 has the much more higher rut depth developed than the other two. But based on this criteria, they are all very good in terms of a rutting resistance. And also moisture damage, TSR. Okay, so this is also in that mix design stage, you have to verify whether this mixes they are good in terms of moisture resistance. So basically, we are using that TSR, tensile strength ratio. So you have your conditioned strength, and also you have your dry condition strength, and you take the the ratio, and the minimum should be more than 0.85, but this one is just less than the 0.85. But other than that, they are all pretty good in terms of moisture damage, right? So also we have cracking resistant test. So we have run like three different kind of cracking test. We have an overlay tester, and also we have a beam fatigue, and also we have our I-feed test. They are actually, different. Of course, they are different device and different parameter you are using. But temperature is pretty much like a very at room temperature, 20 or 25. For example, if you look at an overlay tester, we are using that cycles to failure to categorize the cracking resistance. But if you're looking at a beam fatigue, we are also using that cycles, right? So say how long your material can withstand that under very different kinds of loading. And also with I-feed is a little bit different. It's not like a fatigue, it's just monotonic. So you just actually break the sample in very sudden loading. So and you end up with get a fracture energy and also a phi as your cracking resistant parameter. So this is a typical the results from I-feed, right? So you get the fracture work, the energy, whatever, and also you have that M value. So it's a combined parameter trying to look at the flexibility and also how flexible the material it is, right, to resist the cracking. We also have beam fatigue results here. If you just look at this is the yellow dot, that's the 1C3. they're showing actually better fatigue cracking resistance because they had a higher the cycles of to failure. So, and also, as I mentioned earlier, that 163 had a little bit higher asphalt content, right? So it's like 8% versus 7.7%. So if you have a little bit higher asphalt content, actually going to improve your fatigue resistance for mixes. If we put everything together, iFeed, overlay tester, and also beam fatigue, you can see the ranking, they are very similar, right? Except that the fracture energy, you get a little bit different, ranking results. But other than that, they get a very good, consistent comparison results. The 163 has the best cracking resistance, but 147 has the worst. Okay, so we have some photos from the construction site, and this is for the level binder. As I said, you're gonna put the level binder course, and then you put the surface, the overlay, right? So, and then we did some survey to see what is going on in the field, if there's any cracking or any distresses developed. So this is the one that is showing that just after, just less than one month, and you see the cracking develop, which is the reflective cracking. And also we are get all the data here. Of course, it's a big table, but what you can look at here is just that the 3 contractor, and this is a 133 mixes has the best cracking resistance because it has least the crack length. So if we put performance and also field data together, you can see they have a very good consistent, between the lab test results and also the field ranking. Okay, so this is for the level binder part, as I mentioned. So, and we can see some findings, but I don't see this is a conclusion yet because the project has not done completely, but we can see some findings here. So basically, the ABR cannot always be detected by E-star. As I said, E-star is just focused on the non-destructive range. Is that you don't go to that destructive range. So, and also the level binder should be highly flexible to control cracking. You can see that in our case, even though just like less than 1 or 2 years, we see the cracking here. So which means that if you put a lot of wrap and rest in our level binder course, you may end up with a lot of cracking. And also you can see if you just get a little bit more asphalt content, but not a lot, but you can improve that durability and also the fatigue resistance. And overall, we can see that iFeed, overlay tested, and also that beam fatigue get a very consistent results among these 3. Of course, we're always saying that iFeed gives you a better one because it's easy. It's don't like the beam fatigue takes forever to finish all the tests. And also, we have to use that optimized design to consider how we design the level binder course. And of course, this is the FI should be about 15 for level binder. This is our opinion. Of course, you need to be further validation. And also, we have to consider that how we can put a lot of wrap and rest in our level binder course. Need to be very careful because we don't want to compromise our performance in the field. All right. So now I'm going to move to the surface mix, which is the overlay, and also we are going to talk about mix design, the lab performance test, and also field performance, and also some findings from this overlay mixes. Of course, we have a lot of projects. They are 2014, some are 2015. So they have different ABR and different PG grading binders, and also the contract, they have different traffic volumes. So of course, they also have different pavement structure. What we are doing here is trying to look at 2 things. One is the field performance. So we run a lot of distress survey before the construction, that's a pre-overlay, and also post-overlay, which we have 2 round of field distress survey here. And also we have our lab mix performance test. We are focusing on 3 things. One is the E-star, of course, and also cracking. We are using the overlay test and also iFeed. And also we are running the rutting using the 2. But as you know, that we also have some field course. But for the field course, we just run that iFeed and also the Hamburg wheel tracking because these two we cannot run it because need a very different dimension for the spaceman. So this is a E star here. I didn't plot all the mass curve here, but I tried to using a different parameter to look at it in different way. So I using the E star times time phase angle at a room temperature 21 as a fatigue parameter, right? So if this value is get higher, then you have a worse fatigue resistance. So when we put all the mix together, we cannot do easily comparison. So we just put into different groups. So for example, if you look at a group 2, if you compare these two mixes, you find this is a 157 had a lower E star time phase angle than the 156, which means this one has a better fatigue resistance. So basically, if we put also mixed design information here, we found that if we get a softer binder, for example, if you look at these two, group 1, so this one has a soft binder because the low PG is -34. You have a soft binder, so you end up with like a lower E star time phase angle, which means that you have a better fatigue resistance. And if you look at these two, also the same way, even though the ABR is higher, but you are using soft PG, soft binder, so you get a better fatigue resistance. And also you get a higher AC. For example, if you look at this group 3, right? So one had 60.6, but the other one is like 5.5. So the 1% difference, that's a lot. So you can see that the fatigue resistance is improved by adding a little bit more, asphalt content. And also we get another parameter, which is E star over time phase angle. So that's the rotting parameter. So you get this value is higher, then you have a better rotting resistance. But in this case, you really can see, because, for example, these are three groups. They are very close, right? And also get a very high variation. So I would say it's very hard to just use E star over time phase angle at a 54 such a degree to distinguish mixes in terms of rotting resistance. Okay, so this is the overlay test results. So what you can see, even though the overlay test they have a very high variation for some mixes, for example, say 159, but you can see these two, you get a softer binder, then you still get a higher failures, cycles to failures, which means that if you are using a little bit more softer binders, you end up with like a higher or better cracking resistance. And also, if you compare these two, right? So one has very high, a little bit higher AC content, then you end up with like very much better cracking resistance. So we can see that if you using a little bit softer binder and also relatively higher asphalt content, so you give your mixes to have a better cracking resistance. Also, I-feed test results. So this is the A5. We can see from the similar findings as the overlay tester. So you have the softer binder and also higher AC content for group 3. So you get a better cracking resistance. So if we actually plot I-feed versus the overlay tester, so you get a pretty good correlation. So if you get a higher failure, cycles to failure from overlay tester, and then you can also see that a higher A5, so which means that you can use the, either of those to categorize that cracking resistance of your mixes. Of course, and also rutting performance, that's a little bit different here. We're also using that flow number and also Hamburg wheel tracking. This is a two-line, that's pretty much like a threshold, right? So if you are, for example, flow number, we want a flow number higher, you get a better rutting resistance. So in this case, the minimum should be 50 for the traffic ISO 3 to 10 million. So you see they are much higher than 50. So which means all the mixes, there's no any issues for the routings, right? And also if you are using the Hamburg wheel tracking, so the I dot that threshold is 12.5. So all the rot depths is far below that threshold line. So we are seeing that all the mixes, they have very good rotting resistance. So which means that if you put a lot of wrap and rest in your surface mixes, and you end up with a very high rotting resistance. Okay, so we also compare these two different animals, even though they're the same mix. One is the PMLC, which is the plant mixed laboratory compacted, and also PMFC, which is that plant mixed field compaction. So that's the field core. So of course they have a difference, right? So one we are using geometric compactor to compact those, and the other just to use the roller and do the field compaction. So we are trying to compare what's the difference of these two, right? So this is one of the results from the iFit test. The orange bar, they're all the field core, right? I mean, the blue one, they're all PMLC, the plant mix, the laboratory compacted. And we all see that general trend that the field core had a higher FI than in the lab, right? So which means that in the field, your mixes tends to be softer than the one that we prepared in the lab. Also, I mean, these numbers are showing that air void, right? We want to see whether this air void is actually going to play the significant role in this difference. But you really don't see that clear trend that how the air void is going to affect those FI. Of course, we need a little bit more investigation to see why this is the field core has a much higher FI than the one in the lab, right? And also the fracture energy. The interesting that if you put an error bar here, I would say they are pretty comparable, except field mixes. So which means the FI, FI is a combination of that fracture energy and also the M value. So we are seeing that fracture energy is very close for between the plant mix and also field core, but from the FI we see the difference, right? So this is the Hamburg wheel tracking test results. So we are using the rod depths at 7,500 cycles, and what you can see is that for some mixes, right? For example, the field core had a higher rod depth than the one in the lab. So I think the similar trend, you can see that a field core tends to be softer than the mixes in the lab. But of course, some mixes, they're pretty close. I mean, for example, for group 2, you see that they're pretty comparable. But some mixes, you can see that the field core, is softer than the one in the lab. So, so this is the field performance that we measure the rod depths, and we put everything here. But even though you see a little bit difference, but they are too small. All the rod depth is less than 1 millimeter. So basically, you barely can see them in your naked eye. So, which means that all the rotting resistance for all the mixes are pretty good in the field. But for the transport cracking, right, the field performance, and we see that there's a 2-round survey, and of course, for the first round, there's just a little bit. But I mean, after second winter, and you see some mixes that develop a lot of cracking, right? So why is that? It's because of the construction, or because of the mixes property, or because of the pavement structure. What we found here is that could be the mixes problems here. So if we plot that of FI of the plant mix versus the transport cracking from the first round distress survey, and you can see there's a very clear trend that if you have a higher FI, so you have a much less cracking, right? So if you have very low FI, then you end up with a lot of cracking here. So we are trying to use the 8 as the minimum FI, so we only have 3 mixes, are passing this threshold. And if you look at another FI of the field cores, right? As I said, the field core has a much higher FI value than the plant mix. That's why you see this is like more than 15, right? But if you compare these two versus that FI of the field cores versus that the second round of transport cracking, and you see a good trend here, except this one. This one has the, I would say it's outlier. That's the 159. So there's very high FI values there. And basically, you have higher FI in the field, and also you get less transport cracking, right? So we need also do more investigation to see how we're gonna consider that a field core which they had a very high FI values. But when we put everything together, right, this is just a correlation, say rutting parameters. So we have a lot of rutting tests, flow number, and also Hamburg, and also we have E star over sine phase angle. And you see some trend, but not very good correlation. And also if you look at cracking parameters here, of course iFit is pretty good. Good correlation with the overlay tester. But this E star, is not correlated with the iFit or the overlay test. As I said, the E star is again, in the non-destructive range, right? So you have a cracking test, which is just beyond that point. So they won't see a very good correlation. But if we compare material property with your field performance, which is the cracking, and you also see that overlay tester had a good correlation with the transfer to cracking, as well as that iFit has a little bit better than the overlay tester, 0.72. So that's the correlation between the test parameters and also with the field performance. And some findings here, we can see that if you have a soft binder, so which means that you are using lower PG, and you get a little bit higher asphalt content, you can improve your mixes the fatigue resistance. And we also see that the overlay tester results had a good correlation with that iFit, and also both of them are correlated with the field transfer to cracking. No rutting issues, right? Because we put a lot of rutting rest in the mixes that become very stiff, and also our pavement structures, there are a lot of concrete beneath, so it's also you end up with very low rutting developed in the field. And iFit, of course, is a simple test. It can distinguish different mixes. Okay, so back to the question here. So, how many waste can you put into asphalt pavement, right? Okay, I think you can put as many as you can, as long as it performs well, right? So, we have to use all the material, testing, no matter fatigue or transfer cracking or whatever rutting performance, as long as you can prove that, of course. Especially using the field data to prove your mixes, then you can use that, freely. So, all right. So that's all, and thank you. This is the photo actually I took that last year. That is in the morning, so you can just outside ICT, so you can see pretty good view, right? It's the sunrise here. So, all right. So now I would like to take any question from you guys. Thank you.
It was a really nice presentation. So my question is going to be about comparing the field mixes with the lab mixes. So you said that flexibility in the index of the field mixes are higher than the lab mixes. And I was wondering, I'm going to ask more comments on this, which variable do you expect more in the field mixes, the fracture energy or the slope? Why you get higher flexibility indexes from the field mixes?
I think one thing that here is that the thickness is different. I didn't correct the thickness, right? In the lab, we are compacted 50 millimeter, right? The thickness. But in the field, it ended up with like a 35 or 38. They're varying. So you have a thinner spacement, right? So you are, naturally get a softer for the samples, right? So that's the one thing. The other way, I think that's a compaction efforts. It could be different. In the lab, we are using a dry compactor, but in the field, we are using that roller, right, with the compaction. And if you look a little bit more, I would say the aggregate arrangement, the aggregate, how they actually gonna lay down in the spacements could be also different between the lab and also in the field. Back to the question that you are talking about the iFit results, right? As I showed that earlier, the fracture energy, they are pretty close, right? You see, there's if you put all the mix together, and you see that every ball, I would say they're comparable. Of course, the M value, right, that inflection point there could be different. That's why you see that in the field course had a higher FI than the plant mix in the lab. So.
Than the field mixes.
Yes.
That's
Yes. Yes, yes, but I didn't show the slope here. But of course, that's the fact that yeah, the slope is less than the pound mix in the lab. So yeah.
Uh, Question on leveling binder. So we saw the mixes with the leveling binder has a lot of recycled material.
Yes.
Right. The purpose of leveling binder is to remove that reflective cracking which is coming. So don't you think like why should we use recycled materials at all, especially in the leveling binder?
Yeah.
Like its purpose is to stop the cracking which is coming from the lower PCC. So if we don't have a recycled binder, maybe it's much softer and might resist the cracking. What are your comments on that?
Yeah. Because we didn't design the mixer. That's the mixer design. That's the IDA design. So we're trying to use our expertise, say, or the performance test, to see that you can put a lot of wrap and rest in the level binder. Of course not, right? So you see that a lot of cracking, and also FI is pretty low. So one of the suggestions that we should examine the performance before you put a lot of wrap and rest in the level binder course, because we want to make sure that performance is good. That's why even though you can put anything in the asphalt pavement, right, as long as you can prove that the performance is good, especially long-term performance, not just in the lab you are saying that plant mix they're okay, but also if you have like a long-term age and the other, so you can see the difference, right? So yes. Anything? Yeah, Scott.
No, you had a PhD.
That should be done by Hassan. He was late, so. Yeah, of course. Yeah, I need that handouts, right? There's, I mean, yeah. Originally come from China, so I got my master. Yeah, of course, master and also bachelor degree in China, and then I went to Washington State in 2011. So Washington State University. So I got my PhD there, and also what else? That's all, right? Basically, I spent like 4 years actually working in the lab, day to nights. Basically, even though I was doing a project about the long-term performance of wall mix asphalt pavement, so that's a lot of testing. We had 28 projects across the United States, and we had a lot of field calls. Actually, I think thousands of field calls and sent to our lab. I think just the two of us, actually, basically, me and my co-workers. So we just end up like doing a lot of testing about like E-star and IDT, low temperature, high, room temperature, and also we do binder extraction recovery and also do all the binder tests. So it's a really big one, and basically, that's my life, basically working in the lab. So here is much better for you guys, right? You don't like for example, like when I was in Washington State, our classroom just on top of my lab, because my lab is just in the basement, right? So after you finish the test, then you go up to take your class, and after you finish your class, then you go down your basement and working on the test. So it's more convenient. But here, I think you have to commute between your lab and also the classroom and also your life, right? So you need a little bit more like a balance. Just like for our mix, you have a balanced design, right? Also in your lab, you also need a little bit of balance. But I think it's pretty good, right? You have a research engineer, right? You have me and also Greg. We didn't have any research engineer at that time. So anything that we have to find a way, we have a problem. So of course we always make a trouble. So don't be afraid of to make a troubles, right? Because you have us. We can help you guys to solve the problems, right? But don't make a big one. A small one, I think we are okay with that, right? So you don't want us to get mad, right? So sometimes, but anyway, so I mean, if you have any questions, so just let me know.
Much better than my introduction. Going back, maybe just if you can maybe presented a lot of data from your project, and many of the students are working in this project, but I mean, you have a lot of experience with the materials, construction. You also alluded in one of your slides that the performance can also be affected by structure, construction, and existing condition of the pavement. So given that you have all of this data, and it looks like when you present all of your data, that those mixes are not really so different from each other, right? They are coming from the same type of aggregates, same source of aggregates, similar binders, different grades. Sometimes there's one PG grade difference, but I'm not sure if you look at the continuous grade, maybe they may also be so close to each other, right? Those binder grades. And they all have significant amount of ABR in them. None of them are virgin material, right? So they are all alike mixes. And do you really think that the material itself could really be attributed to the differences in the performance in this project?
I would say that
The performance differences are big. You know, you're jumping from, especially when you present the transverse cracking, is a huge performance differences, right?
yeah. I would say, if you just look at FI, right? FI is the good indication for the transfer cracking. That those mixes, which had a very low FI, that you end up with very high cracking in the field. But I think your question is to go back to mix design. I mean, maybe there's something, different that we don't know. As we said, maybe the PG, they are just different. Because we never actually test the PG grading, right? We never actually know that gradation is really the gradation they're designed for. Maybe there's something wrong in the field. That's possible. But I think based on what we have so far, I would say, if you just run FI, no matter what kind of mix design you have, it could be have a higher asphalt content, higher PG grade, and also get a different thing. But FIs give you like overall indication, for the cracking resistance. So
I think I just my maybe point I was trying to make in here is that mix designs, they're coming from professionals, and those are the things that they've been doing for a long time. Is there may be some minor difference that makes those lab performance can be slightly different from each other. But overall performance, it looks like they're very good rut resistant mixes, and none of them really suffer from rut resistance. Modulus, they're all close to each other. There are some differences in the crack resistance and propagation, some differences, but not also really huge margins. They're also relatively close to each other. So that's why I think, especially when it comes to cracking and for overlays, and you mentioned the structure, existing condition of the pavement, and also the other factors.
Yes.
Because that maybe because those are things that you have data. You didn't present it in here, but maybe next time when you have a chance to present, maybe and everything you presented together, you get a better understanding of what really contributes to this performance difference.
yeah, I think you have very good comment here that in a field, again, when I was dealing with the field data, you had so many variables, right? You have a traffic level, you have pavement structure, and also you have reclaiming. Of course, in this case, reclaiming is very similar, but there's a lot of variables here. So I would say it's not that easy. We are trying to find out. Sometimes you see that is that actually the age could be the significant factor. Say you have a higher aging, years, right? You can end up with a lot of cracking, right? But sometimes not. It's totally dependent on data you collected. Sometimes, maybe they are not significant. Some are not significant, some are not. So it's really need a method that you can actually find out what's the most significant to affect your performance, right? Transfer cracking. But now, of course, today I'm just to present the material property. I would say I just ignore those factors. But I think that's a good way to go. We can explore more. Of course, students also can spend the time to looking at those very challenging work, because every time you end up with like a regression or anything that you are trying to combine everything, consider everything, traffic, pavement structure, existing pavement. You need to really be very careful, because people always don't agree about that because they have their own opinions. But what I'm saying is that we need to look at what are most significant, which are not. Maybe it's not just regression itself. Maybe it's something that we do analysis work. So that's the way we can go. But yeah, I think that's a very good comment. So I think we can actually work together, to figure it out. Hopefully, we can have a good ending for this project. That's my hope. So, right? Yeah. Thank you.